Let's design Chapter 8, Design a unique ID generator in distributed systems. Starting with our system requirements, there are a few core properties every ID must satisfy. IDs need to be unique and sortable. They should increment by time, meaning a newer ID will always be larger than an older one, but they don't need to increment by exactly 1, gaps are acceptable. IDs must contain only numerical values, no letters or special characters. Each ID must be exactly 64 bits in length. And the system needs to be capable of generating 10,000 IDs per second. Now let's break those down into formal functional and non-functional requirements. On the functional side, we have uniqueness. All generated IDs must be globally unique across every distributed server in the system. We have sortability. IDs must be sortable by time, which is why the time-based increment property matters. We have the numeric-only constraint, meaning IDs are pure numbers. We have ID size, fixed at 64 bits. And we have throughput, which requires the system to support generating 10,000 IDs per second. On the non-functional side, we need high availability. ID generators are a critical dependency for almost every other part of the system. If they go down, nothing can create new records, so they must be highly available. We also need to address clock synchronization. In a distributed environment, different machines and CPU cores may have slightly different clocks, which can break our time-based sorting guarantee. Network Time Protocol, or NTP, can be used to resolve these inconsistencies and keep clocks aligned across the system. Finally, let's look at how the 64-bit ID is actually structured to meet those requirements. To hit 10,000 IDs per second, we need enough bits dedicated to sequence numbers and enough timestamp resolution. The timestamp field uses 41 bits, representing milliseconds since a chosen epoch, either the Unix epoch or a custom one. 41 bits of milliseconds gives us a maximum lifespan of roughly 69 years before the timestamp overflows. The datacenter ID field uses 5 bits, which supports up to 32 distinct data centers. The machine ID field also uses 5 bits, supporting up to 32 machines per data center. Together, the data center and machine IDs ensure that two different machines generating an ID at the exact same millisecond will still produce unique values. Let's walk through the core entities. First up is the unique ID. This is a 64-bit numeric identifier, and it has 3 important properties: it's unique, it's sortable by time, and it's generated in a distributed fashion. That last part matters a lot, because we're not relying on a single database to hand out IDs. We need a structure that lets many machines produce IDs independently while still guaranteeing no collisions and preserving time ordering. Next is the data center. A data center is a physical or logical grouping of machines, and it's identified by a 5-bit data center ID. That 5-bit field gives us up to 32 distinct data centers. This ID is assigned at startup time, meaning it's baked into the configuration when the service comes online rather than being negotiated dynamically. Closely related is the machine, or server. Each individual server within a data center gets its own 5-bit machine ID, also assigned at startup. Combined with the data center ID, this pair uniquely identifies any single machine across the entire infrastructure, which is what allows each server to generate IDs without coordinating with others. Then there's the ticket server. This is a different approach entirely, a centralized server whose sole job is generating unique primary keys for use across multiple services. Rather than every machine doing its own ID generation, services make a call to this central authority. It trades some scalability and fault tolerance for simplicity. Finally, the sequence number. This is a per millisecond counter that lives on each individual machine. Every time a machine generates an ID within the same millisecond, it increments this counter. When the clock ticks over to the next millisecond, the counter resets back to 0. This is what allows a single machine to produce multiple unique IDs within the same millisecond without any coordination. Let's walk through the data flow. 2 pieces of information are decided up front, at startup time, the data center ID and the machine ID. Everything else gets figured out on the fly, at runtime, each time a new ID needs to be generated. So let's go through how each part of the ID is composed at runtime. First, the sign bit. This is always set to 0. It doesn't carry any meaningful information right now, it's simply reserved for potential future use. Next comes the timestamp, which takes up 41 bits. This records the current time in milliseconds, measured either from the standard Unix epoch or from a custom epoch you define. Using a custom epoch is a common choice because it lets you squeeze more useful lifetime out of those 41 bits by starting the clock closer to your system's launch date. After that, you have the data center ID, stored in 5 bits. This identifies which data center the generating machine lives in. Then the machine ID, also 5 bits. This identifies the specific machine within that data center. Together, these two fields are what guarantee uniqueness across your distributed infrastructure. No two machines in the whole system share the same combination. Finally, the sequence number. This is incremented by 1 every single time a new ID is generated on a given machine. If multiple IDs are requested within the same millisecond, the sequence number keeps climbing to keep each one unique. Then, when the clock ticks over to a new millisecond, the sequence number resets back to 0 and starts again. Now let's walk through the high-level design section. We have 4 candidate approaches to consider: multi-master replication, universally unique IDs also known as UUIDs, a ticket server, and the Twitter Snowflake approach. Let's go through each one. Starting with multi-master replication. This approach leans on the database's built-in auto-increment feature, but with a twist. Instead of incrementing each new ID by 1, we increment by k, where k is the total number of servers. So if you have 5 servers, each one jumps its counter by 5 with every new ID it generates. This distributes the work across servers and avoids the bottleneck of a single machine handling all ID generation. However, it comes with real drawbacks. It's hard to scale across multiple data centers, because coordinating the increment logic between geographically separate clusters gets complicated quickly. IDs also don't increase uniformly over time across servers, since each server is generating its own sequence independently. And perhaps most critically, adding or removing servers breaks the mechanism entirely, because the value of k changes and the sequences no longer stay non-overlapping. Next up is UUID. A UUID is a 128-bit unique identifier. The probability of 2 UUIDs colliding anywhere in the world is astronomically small, so uniqueness essentially isn't a concern. An example looks something like 09C936250B446ADBF8AC071040BFB2. The big advantage of UUIDs is that each server can generate them completely independently, with no coordination or synchronization needed between machines. That makes them very easy to scale. But there are meaningful downsides. At 128 bits, they're too large for our requirements. They don't increase with time, so you lose any natural ordering. And they're non-numeric, which may not be acceptable depending on the system's constraints. Now let's look at the ticket server approach. A ticket server is a centralized, dedicated server whose sole job is to generate unique primary keys for all the other services that need them. On the plus side, the IDs it produces are numeric, and the whole setup is straightforward to implement. It works well for small to medium-scale applications. The problem is that this centralized design creates a single point of failure. If the ticket server goes down, nothing can get a new ID. There's also the matter of additional latency introduced by the network call every service has to make to request an ID. Finally, the Twitter Snowflake approach. Twitter's Snowflake design meets all the key requirements. IDs are 64 bits, they're sortable by time, and they can be generated independently on each server without any coordination. The 64-bit ID is divided into several distinct sections. The first is a sign bit, which is always set to 0 and is reserved for potential future use. Next comes the timestamp, which occupies 41 bits and represents milliseconds since a chosen epoch. This gives a maximum range of about 69 years. After that are 5 bits for a data center ID, supporting up to 32 data centers. Then another 5 bits for a machine ID, allowing up to 32 machines per data center. Finally, there's a sequence number. Every time an ID is generated within the same millisecond on the same machine, the sequence number increments. It resets back to 0 at the start of each new millisecond. Now let's get into the deep dives. We'll be using Twitter's Snowflake algorithm, as it fits our needs best. We explored multiple approaches to generating unique IDs and landed on Snowflake because it serves our purpose better than the alternatives. Let's talk through a few important considerations when running Snowflake in practice. First, clock synchronization. Because Snowflake relies on timestamps, different machines or CPU cores can have slightly inconsistent clocks. Network Time Protocol, or NTP, can be used to resolve these inconsistencies and keep everything in sync. Second, section length tuning. The bit layout of a Snowflake ID isn't fixed in stone. If your application has low concurrency but needs to operate over a very long time horizon, you could sacrifice some of the sequence number bits and allocate them to the timestamp portion instead, giving you a longer time range at the cost of fewer IDs per millisecond. Third, high availability. ID generators sit in a critical path, almost every write operation depends on them. That means they must be highly available, with redundancy built in from the start. Now, why not the alternatives? With multi-master replication, the approach is hard to scale across multiple data centers. IDs don't increase monotonically in time across servers, and adding or removing servers can break the entire mechanism. UUIDs are 128 bits, which immediately violates our size requirement. On top of that, they don't increase with time and can be non-numeric, both of which are problems for our use case. A ticket server introduces a single point of failure, and every ID request requires a network call, which adds latency. And finally, why a primary key with auto-increment won't work. When you're generating IDs across multiple database servers, the coordination required introduces high latency, making it unsuitable for a distributed system at scale. Wrap up. We explored multiple approaches to generating unique IDs and ultimately settled on Snowflake as the solution that best fits our needs. Now, a few important talking points worth keeping in mind. First, clock synchronization. Because Snowflake relies heavily on timestamps, clock drift between different machines or CPU cores can become a real problem. Network Time Protocol, or NTP, is the standard tool for keeping clocks consistent across a distributed system, and it should be part of any serious deployment of this design. Second, section length tuning. The bit layout we discussed isn't set in stone. If your system has relatively low concurrency but needs to generate IDs over a very long time horizon, you could trade some of the bits allocated to the sequence number and give them to the timestamp instead. The right balance depends entirely on your specific traffic patterns and longevity requirements. Third, high availability. ID generators sit in a critical path, almost every write operation in your system depends on them. If an ID generator goes down, requests stall. That means redundancy, failover strategies, and careful operational monitoring aren't optional here, they're essential.